Okay, so start. Okay, so today we'll solve the assignment 9 for the course Linear Algebra NOC 23 MA03. Okay, let's start with the first question. So what is the first question? Saying that which of the following vector space V is an inner product space with respect to the inner product which is defined below on V cross B. So you have to check the following options in among them which are inner product, right? So the first option is it's V is the complex number C. It's over R. We have to check Z comma W inner product is defined real part of Z into W over, right? So you have to check this is inner product or not. So this is question number 1. If the vector space B is the complex number C, and we have to check over R, the field is R, and the inner product is defined Z comma W. It's real part of Z W over, right? So what are the conditions to satisfy this two inner product? First, we have to show additivity, means you have to take Z1 comma Z2 from and W from C. These are the vector. You have to check that this is true or not. Z1 plus Z2 comma W. You have to check that this is Z1 comma W plus Z2 comma W. This is true or not. So let's check this. So left hand side what it will be? LHS Z1 plus Z comma W means it will be real part of Z1 plus Z comma W bar, right? And now the product, this is distributed for complex number, so it will be real part of Z1 W bar plus Z2 W bar, right? Now real part we can take it also, this is so real part of some this plus this means real part of first one Z1 W bar plus real part of Z2 W bar, and this is the so real part of Z1 W bar means this is Z1 W bar plus this is Z2 W bar. So which is the right RHS, right? So the first condition is satisfied for inner product. Now what we have to check? Now the next condition. So this is the condition number 1. Next you have to check Z W bar or WZ bar, you can call it to, means ZW equals to WZ bar, right? This we have to check. This is the next condition. So let's check this. Z comma W. This is the real part of ZW bar. Now real part. So let's start from the right hand side. It will be easier then. So what is right hand side? RHS. So RHS is WZ bar. So it will be real part of WZ bar, this bar, right? And now this is real, right? So bar and it will be same. For the real part, Z and Z bar are same for real number. So this is same as real part of WZ bar, right? And real part of Z and Z bar are also same. So this we can write real part of WZ bar whole bar. Why this is true? As real part of z equals to real part of z bar, right? So now bar, so it will be real part of it will be z w bar, right? So which is the left hand side? So again the condition 2 is satisfied. And what is the third condition? Third condition is it's z comma z. We have to check. This should be non-negative, right? So what is z comma z? For two same number, z comma z, it is real part of z bar, and z bar means it is real part of mod z square, right? And mod z square for if z is non-zero, so this is strictly positive if z is not zero, right? If z not zero, then mod z is strictly positive, so real part will be, so and mod z square is always positive, so it will be right. So condition 3 is also true. Now check, we have to check the condition 4. So what is the condition 4? Take, so this we have to check the inner product space over R, right? So this we have to check over R. So you have to check scalar for real scalar, right? So take C real number, and we have to check C Z W what it will be. So this is means this is by definition a real part of CZ into WR. Now what is this? So real part. So as C is real number, so C you can take it out. So C it will be real part of ZWR. And what is this? So this is C. This you can write ZWR. Z inner product with W, right? So condition 4 is also satisfied. So you checked all the condition for inner product space. So means the first one is so therefore Z comma W, which is defined by real part of ZW is an inner product over R. So first option is correct. Now let's check the next option. What is? Yeah, the vector space is C2, and we have to check it's a over C, vector space is over C, and the inner product is defined Z1 comma Z2, and with W1 comma W2 is Z1 W1 plus Z2 W2. So let's check this. So this is question option number 2. What is vector space is C2 over C, and what is it is Z1 comma Z2 comma W1 comma W2. It's Z1 W1 plus Z2 W2. So you have to check this this is an inner product or not, or what C. So what are the conditions? So we show that this will not be an inner product on the vector space C2. So for that we have to show that at least one of the condition for the inner product is not satisfied. So let's check the positivity condition. Means if we take the two number Z comma Z, then it is not always non-negative. So let's take two vectors. Take one such that, take this 0 comma I. This is on C2, right? This is on C2. So let's, what will be the this inner product? Let's check 0 comma I comma 0 comma I. So this is by definition. So this is Z1, this is Z1, Z2, this is W1, W2. Means here it is Z1, Z1. So it will be Z1 W1 means it's 0 dot 0 plus it will be I dot I. So it's I square means it's minus 1. So this is not strictly positive, right? So it does not satisfy the condition of inner product positivity. So means, so for inner product note, so this is note for inner product Z comma Z should be strictly positive, right? So this is not true here. We have taken same vector 0 comma I comma 0 comma I, but this is not minus 1, which is not positive. So this does not satisfy the condition of inner product. So this is not an inner product. So V is not an inner product space. With respect to this inner product. Right. So the option number 2 is false. Okay, let's check the option number 3. What is option number 3? Vector space is Rn over R and two vectors. It is x1 yn, x2 yn minus 1 and xn y1. So let's check this. What is this? Vector space is Rn over R, and how the inner product is defined? X1 dot 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 xn comma y1 dot 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 yn. It's x1 yn plus x2 yn minus 1 plus dot 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 xn y1, right? So you have to check this is inner product or not. So again we show that this is not an inner product space. So again we check the condition number 3 means take two vector and show this is not satisfy the positivity condition. So let's take the vector v2 is 0 or 1 1 1 0 0. Take the 1 0 0 0 0 0 0. This belongs to Rn. Let's check this v comma v. So this will be 1 0 0 0 0 0 comma 1 0 0 0 0. Then by definition it is x1 with yn, it will be 1 dot 0, right? Plus x2 yn minus 1, it is also 0 dot 0 plus dot 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 all other term, because the first vector all other term is 0, it will be 0 dot 0, right? Or 0 dot 1 it will be for the, so it will be 0 dot 1 means it's again 0. So this is not strictly positive, right? So it does not satisfy the condition number 3. Does not satisfy the condition for inner product. So V is not an inner product. Space with respect to this inner product. So option number 3 is again false. This is not an inner product. Now option number 5, this is vector space Pn, set of all polynomials of degree less than equals to n, and inner product Fg is defined. It's the Riemann integration of f dot g on from 0 to 1. So this is option number 4. So V is PNR over R, and how the inner product is defined? F dot F inner product with G integration 0 to 1 Ft into Gt dt. Yes. Okay. So now let's check that this is inner product or not. So you have to again check all the condition. So we will show that this is an inner product space. So let's check. So first you have to check the additivity. The option number 1, take FGH from PNR. So you have to check this F plus G inner product with H. So what is this? So integration 0 to 1 Ft plus Gt into Ht dt. Now integration, it is additivity, integration of the additivity of the Riemann integration. So first one, it will be 0 to 1, it will be Ft Ht dt plus 0 to 1 Gt Ht dt. So this is the F inner product with H plus G inner product with H, right? So this satisfies the first one. Now let's check the next one. Option number 2. What is option number 2? So we have to check that here it is real. So for the real inner product space, there is no bar. So this condition is automatically, so Z. So you have to check this ZW, sorry, Z, it is all the functions. So Fg is 0 to 1 Ft Gt dt. What will be this? So this you can write, because this you can write Gt Ft dt, right? So this is same as G inner product with F, right? So Fg equals to Gf. So this satisfies the condition number 2. And condition number 3, what it is? You have to check F inner product with F. So it will be 0 to 1. It will be Ft whole square dt. And this will be positive if F not 0, right? Because it will be, if F is not 0, then because these are all polynomial, so you can find because continuous, so there will be one neighborhood on which this is non-zero. So on that neighborhood, so note as F is polynomial, so F non-zero means there exists a neighborhood on which f is not 0, and for that their integration will be positive, so the inner product will be positive, right? And the condition number fourth, so you have to take C real number, C f g. So what it will be? It will be integration 0 to 1 C f t g dt. And now you can take C to be take it out, 0 to 1 f t g t dt. So this is C f inner product with G, right? So this also satisfies the condition number 4. So means this satisfies all the conditions. So this is an inner product. So this is an inner product, right? Okay, so option number 4 is also correct. Now let's check the option number 5. What is option number 5? It's B is MNR, and the inner product is given by A inner product with B is trace of A minus B. So what is the option 5? B is MNR and A inner product with B, it's trace of A minus B. So you have to check this is an inner product or not. So let's take A non-zero, and so take A non-zero such that take A non-zero, and now compute this A inner product with A. So what will be this? Trace of A minus A, right? So this is zero matrix. So trace of zero matrix. Trace of zero matrix is 0. So for this same A inner product A, so this is 0, means this does not strictly positive. So this is not an inner product. Okay, this is not an inner product. Okay. So option number 5 is incorrect. And option number 6, this was done in the class that B with MNR, inner product B, trace of A transpose B, this is an inner product. So I leave it to you. Means also this was done in the class that this is an inner product. So option number 6 is also correct. So question number 1 is done. Let's move to the question number 2. Okay. So what is question number 2? In R2, a inner product is given. Then you have to let the length of the vector B is the in the norm with respect to the this inner product is denoted by norm B. Okay. So let me explain. So vector space here is R2, and what is the inner product? For x1, x2, comma y1, y2. Inner product is given by x1, y1 plus x1, y2 plus x2, y1 plus 6 x2, y2. Right. So this is the inner product. This you can check that this will be inner product on R2. And what is the norm B? How the norm of a vector is defined? So let B is in R2. Then norm B, how it is defined? because this is the inner product. So we define the norm B to be the square root of B inner product with B. Note that for B inner product with B, note on inner product space B inner product B is always non-positive, right? This way, for inner product, this should be the condition for B non-zero. Means for greater than equals to 0, this will be 0 for if B is 0. So this will be true. And if B is non-zero, then this will be true. So this is the norm. So we have to compute the norm of this vector. B is given 1, 1. So let's check here. B is 1, 1. So then what will be the norm of this? Norm B is norm of 1, 1. So it will be square root of 1, 1, 1, 1. And what is the inner product? This is x1, y1, x1, y2, x2, y1, 6, x2, y2, right? So this will be, so x1, y1 means 1 dot 1 plus, it will be again 1 dot 1 plus again 1 dot 1 plus 6, 1 dot 1, right? So this is the by definition of the inner product. And so what is this? So this is 6, 7, 8, 9. Square root of 9 means 3. So the length of the vector is 3. So this is the length. So norm B is 3. Right. So question number 2 is done. So norm B will be 3 for B is 1, 1. And again we have to check in the same question that if B is 1, 0, then what will be the norm? So here B is non-zero means norm B. So norm of 1, 0. So this is square root of 1, 0 inner product 1, 0. What is this? So this is again by definition. What is the definition? x1, y1, x1, y2, x2, y1, and 6, x2, y2. So it will be again x1, y1 means 1 dot 1 plus x1, y2 means 1 dot 0 plus x2, y1 means 0 dot 1 plus 6, x2, y2 means 0 dot 0. So then what will be this? So this will be square root of 1 means 1. So the length of here the norm B is 1. So question number 3 is 1. Okay, so question number 3 is done. Let's move to the question number 4. In the question number 4, you have to check which of the following statements are true. The first option is B be a vector space C over R. Then you have to check what is the dimension of B, that it is true or not. So B is a vector space over R. Option 1. B is C over R. What will be the dimension of B? So over R, note over R, 1 and I are linearly independent. What it means so that is there does not exist a C which is real number such that 1 equals to C times I, right? So this will not hold, means 1 and I are the independent on C over R, right? So these two are linearly independent, and you can check that these two form a basis also. No, 1 and I forms an basis of C over R, right? Why this will be basis? As any complex number Z can be written as Z equals to, you can write A plus IB, right? Where A and B are real number. So this is A dot I plus B dot I. So means, which implies Z is in the span of 1 comma I, right? So these two are linearly independent and they span the whole C2, which implies span of 1 comma I is the whole C. So therefore dimension of B implies dimension of C, this is over R, is 2, right? So the option number 1 is correct. Dimension of B over R is 2. What is the next option? Here you have to check dimension of B, the complex number over C. So here it is saying the dimension of the complex number over C, it will be 1. So let's check this. So this is option number 2. Here B is a complex number over C. Here you have to check that dimension of this complex number over C is 1. So here we will show not over C 1 and I are not linearly independent. Why? Because here the field is C, as we can write I equals to I times 1, right? Where I is a complex number, right? So I and 1 are linearly dependent. So now, therefore over C, so any Z in C, we can write this Z you can write, right, 1 times Z, or 1 is the real number which is the subset of C, right? So therefore, which implies span of 1, this is span of 1 is C, right, over C, which implies dimension of C over C is, sorry, is 1, right? So option number 2 is also correct. Dimension of C over C is 1. Now let's check the option number 3. Here the B is the vector space C and it is over R. How the inner product is defined? A plus IB comma C plus ID is AC minus BD minus I times AD plus BC. that this defines an inner product or not. So let's check this. So V is the vector space C over R. How the inner product is defined? A plus IB comma C plus ID is defined A C minus BD minus I times AD plus BC. Right. So this is the definition of the inner product. So we check this is an inner product or not. So we'll show that this is not an inner product for C over R. So again we check the condition number 3, the positivity condition. So let's check. So here we will take this. Take A plus IB equals to 1 plus I. Right. So A equals to 1, B equals to also 1. So now check this 1 plus I comma 1 plus I. So what will be this? AC minus BD means S squared. So this is 1 minus BD. What is BD? B is 1, D is also 1. Minus I times AD. What is AD is 1 plus 1, right? So this is minus 2I. So this does not, so this is not even real number, right? So this is a complex number. So this is, no need to check that this is positive or not because this is complex number. So therefore, this is not an inner product. Right. So option number 3 is false. This is not an inner product. Now let's check the option number 4. What it is? B is the vector space C over C here. The previous one is B C over R. And the definition is the same. But we have checked the condition number 3 is not satisfied. And condition number 3 does not depend on the field. Means that for that we have to always check that B inner product B is positive. So this does not depend on the field, the condition number 3. So same example shows that. So for 4, same example work, right? Example as 3 will work. Okay, this is not an inner product. So option number 4 is also false. So this is again false. So question number 4 is done. Let's move to the question number 5. Okay, what is the question number 5? B be a real inner product space, means vector space over the R, and S is the be a subset of B is given B1 up to B1 B2 up to Bn, such that 0 does not belongs to S. Then you have to check which of the following statements are true. Okay. So what is the first option? It's saying that if S is an orthogonal set of vectors, then dimension of B is greater than n. So orthogonal B, as B is inner product space, so orthogonality is well defined means. So what is option number 1? How the orthogonality is defined? So as B is inner product space, so two vectors, take V and W in V, we say V, W are orthogonal if V inner product W is 0. This is the orthogonal. So, and S is orthogonal set of vectors means any two vectors V1, inner product Vi will be 0. It's saying that if S is an orthogonal set of vectors, then dimension of V is greater than n, and S contains n many vectors. So we'll show that if S is an orthogonal set of vectors, then S is linearly independent. So what is S? S is V1 up to Vn. And what is given? Given that S is orthogonal set of vectors. So we will show S is linearly independent. So okay, so let's check. So take the linear combination C1 V1 plus C2 V2 plus dot 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 Cn Vn equals to 0. So you have to so that C1 C2 Cn are all 0, right? So let's call it W. Let's call it W. Right. Now take the inner product with V1. Take inner product with V1. What you will get? First note this. So you will get W inner product with V1. So what it will be? W inner product with V1 means C1 V1 plus dot 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 Cn Vn inner product with V1. As these are orthogonal set of vectors, so only V1 will be survive. Other all the inner products will be 0. So it will be only C1 V1 times V1, right? And this is as W is 0 vector, so this side is 0, right? If you take the inner product and 0 vector, it will be 0, right? So C1 V1 is 0, and V1 is suppose non-zero is a non-zero vector, right? Because S does not contain 0 vector. As 0 does not belongs to S, implies V1 is non-zero, right? Which implies V1 is non-zero. So therefore, so this is star. So from star, so this is non-zero means C1 must be 0, right? So when we taking the inner product with V1, we get C1 0. So therefore, taking inner product with arbitrary vector Vi with Vi, what you will get? W inner product with Vi. So this is 0, which you will get C1 V1 plus dot 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 Cn Vn inner product with Vi. Just wait 1 minute. Okay, so what you will get? Just wait 1 minute.
आपके द्वारा डायल किया गया नंबर अभी व्यस्त है। कृपया कुछ समय पश्चात प्रयास करें। The number you have dialed is currently busy. Please try later.
Okay. So what you will get if you take the inner product with Vi? So you will get this time you will be Ci, right? Only Ci will be non-zero. It will be Vi inner product with Vi. And as Vi is in the set W, so you will get, so therefore Ci will be 0, right? So therefore C1 up to dot dots Cn all the elements are 0 implies S is linearly independent. Okay, so we have shown that if S is orthogonal, then S is linearly independent. So as S is in V, so which implies dimension of V is greater than N, right? So the option number 1 is correct. If S is an orthogonal set of vectors, therefore S is linearly independent. So therefore dimension of V is greater than N, right? Equals to 1. So the first option is correct. Now let's check the next option. Fix a vector u in V, then define the linear transformation TV equals to u inner product with V. So you have to check that this is an a linear transformation or not. Okay. So this is the option number 2. checks V is in V or U is in V. Define. Now they define TV is U inner product with V. You have to check this is the linear transformation or not. So first for the linearity, so what it will be checked? We have to check the first one, T of V1 plus V2. So what it will be? It will be U inner product with V1 plus V2. And this, as this is real inner product space, so it is, so you can show that it is additivity with respect to the second variable, right? You can also check that. So this will be U V1 with U V2 means T of, so this is V1 plus T of V2. This satisfies the first option. Now let's check the next one. What is the next one? You have to check the T. If you take the some real number C, CV. So what it will be? It will be U inner product CV. And as this is real inner product space, so C will came out. It will be UV. As V is real inner product space. Otherwise, C bar will came out. As V is real inner product space. So this is C times TV. So this satisfies the condition of linear transformation. So therefore, T is a linear transformation. B to R. So option number 2 is again correct. Okay. Now what is option number 3? So T V is from V to W, be a linear transformation between inner product spaces. And then you have to check that S dash, it is the images of under T which of V1, V2 up to Vn, that this is orthogonal, right? So you have to check that these are orthogonal or not, images of V1 up to Vn. Okay. So let's check the option number 3. So T is from V to W, linear transformation. What is S dash? S dash is TV1 up to dot 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 TVN. You have to check that this is real linear transform orthogonal or not. To check S dash is orthogonal or not. So let's check for n equals to 2. Take for the moment n equals to 2, right? Because if this is not true for n equals to 0, then it is not true in general. So take n equals to 2 and define this t from R2 to R2. E1 goes to E1 and E2 goes to E1 plus E1. With respect to R2 and take R2 with usual inner product. R2 with respect to usual inner product. Right. So then what is S dash? S dash is TU1 TE2, right? You have taken V to V, you have taken S to be E1 E2. Then these are, so what is this? This is E1 and E2, E1 plus E2, right? And this, then they are not orthogonal, right? Not E1 inner product with E1 plus E2. It will be E1 inner product with E1, right? E1 inner product with E1 plus E1 inner product with E2. So this will be 1 and this is 0, right? So this is 1 you will get. Because these two are orthogonal. So implies E1 and which implies S dash is not orthogonal, right? So S dash is not orthogonal. So this is in general not true. So option number 3 is false. So this is not true in general. Okay. So option number 3 is done. Let's check the option number 4. What it is saying? Norm of V1 minus V2 square equals to norm V1 square minus norm V2 square. If S is an orthogonal set. So this is option number 4. If S is an orthogonal set, is norm V1 minus V2 square equals to norm V1 square minus norm V2 square. So you have to check this. So let's check this. So we will show that this is not true. So suppose take this. So on R2, this is not true, right? So on R2 we will show take S to be 1 0 and 0 1. So then what will be, so take this to be V1 and take this to be V2, right? So then what will be the norm of V1 minus V2? So then V1 minus V2, what is V1 minus V2? 1 comma minus 1, right? Then what will be the norm of V1 minus V2 square? So norm of V1 minus V2 square. So it means it is inner product of 1 comma minus 1, right? Comma 1 comma minus 1. So it will be 1 plus 1 means 2, right? Here the inner product is usual inner product with usual inner product. What is usual inner product? Usual inner product is x1 comma y1 with x2 comma y2 means x1 y1 plus x2 y2 on R2. And what will be norm v1 square? It will be, what is v1? It's 1 comma 0. It's the unit vector. So it is 1 and norm v2. It is again 0 comma 1 with 0 comma 1. It is again 1. So what will, so therefore, so what is norm v1 square minus norm v2 square? This is 1 minus 1 is 0. So this is not same as this. So therefore, norm v1 minus v2 square equals to, this is not same as, so this is not true. So option number 3 is false. Okay. Option number 4 is false. Now let's check the option number 5. So this is norm of v1 plus v2 square plus norm of v1 minus v2 square equals to 2 times norm of v1 square plus norm of v2 square for all v1 v2. Right. So let's check the option number 5. Norm of v1 plus v2 square plus norm of v1 minus v2 square equals to 2 times norm of v1 square plus norm of v2 square for all v1 comma v2 belongs to v. You have to check this. So let's check this. So start with the left hand side. Norm of v1 plus v2 square plus norm of v1 minus v2 square. So norm square means it is the inner product with same v1 comma v1 with v1 plus v2. So v1 plus v2 comma v1 plus v2 plus inner product with v1 minus v2 inner product with v1 minus v2. Right. So if you, so what will be then this? So if you compute this, what you will get? You will get v1 comma v1 plus v1 comma v2 plus v2 comma v1 plus v2 comma v2 plus v1 comma v1 plus v1. Oh, so this will be minus v1 comma v2 minus, you will get v2 minus v1 plus v2 comma v2. You will get this. So now check that these two will cancel. These two will cancel. So what you will get? So this is non v1, inner product v1 comma v1 is non v1 square. And this is the same is non v1 square. So you will get 2 times non v1 square plus this is non v2 square 2 times. So non v2 square. So this is the RHS, right? So we have to prove this. So this we have to prove. So option number 5 is correct. So in inner product space, this identity is called the parallelogram identity. So you can note that if you take two vectors, it is v1 and this is v2. Then if you form the parallelogram with this two side, then this will be v1 plus v2. This vector, it will be v1 plus v2, and this vector will be v1 minus v2. Now, what it is saying that sum of two diagonals of the parallelogram is means length of the two squares of the two diagonal same as 2 times the length of the two these sides, 2 times of the sum of the sides. So this is called the parallelogram identity in our product space. Right. So this finishes the question number 5. Let's move to the question number 6. What it is saying? Consider the vector space C0, 1. So means continuous function from 0, 1 to R. So continuous real value functions defined on the interval 0, 1 with the inner product f, g define integration 0 to 1 fx gx fx times gx into dx. Then you have to what are given f, g, two functions are given such that norm of f is 2 given, norm of f plus g is given 1, norm of f minus g is 3. Then you have to calculate the value of norm g. Right. So what we have seen earlier that in inner product space parallelogram identity is true. So we'll use that to prove this. So note that on inner product space on the previous question we have shown on inner product space norm v1 plus v2 square plus norm v1 minus v2 square equals to 2 times norm v1 square plus norm v2 square is always true, right? For all v1 v2 belongs to v. So we'll use this to prove this question number 6. Here v is the vector space, continuous function from 0, 1 to r. C 0, 1 to r. How the inner product is defined? F inner product g is integration 0 to 1 fx gx dx. Right. So you have to, what is given? Norm f's, these are given. Norm f is 2. Norm f plus g is also given to be, well, this is 1. And norm f minus g is given to be 3. So to find norm g, right? So we know, what we know, that this will always true, right? F plus g parallelogram identity. This will always hold on inner product space. So this is 2 times norm f square plus norm g square. So use this. So what will be then? This will be 1 plus 9 equals to 2 times. This is 4 plus norm g square, right? So means what you will get? So this will be 2 times norm g square will be 10 minus 8. It's 2. Or norm g square you will get to be 1, which implies norm g is 1. So we get norm g to be 1, right? So this is the, so question number 6, we get norm g is 1. Question number 6 is done. What is the question number 7? Here the same, with the same question, here fx is given on continuous function, fx is 6x and gs is 1 minus x. You have to find the inner product with fg. So how the inner product is defined? Integration 0 to 1 fx gx dx, right? So then what it will be? 0 to 1, what is fx? It's 6x times 1 minus x dx. So this will be 0 to 1 6x minus dx minus 0 to 1 6x square, right, dx. So if you integrate this, you will get 6 into x square by 2, evaluate from 0 to 1, minus 6 x cube by 3, evaluate 0 to 1, so you will get 6 by 2 minus 6 by 3. If you do this, you will get, so this is 3, this is 2, this will get 1. So you get EF inner product with G is 1. Question number 7 is done. Then what is question number 8? Gx is given cos pi x. You have to find the 2 norm Gx. So what is norm G? Norm G is defined in square root of G inner product with G, right? So first let's find what is G inner product with G. G inner product with G, what is this? So this will be integration 0 to 1 Gx square dx, right? Because gx times gx is gx square. So what will be this? So this is 0 to 1 cos square pi x dx. We have to integrate this. So let's multiply by half and multiply by 2. 2 cos square pi x means 2 cos square theta is 1 plus cos 2 theta, right? So cos square 2 pi x. Now we can integrate it out. So what it will be? It will be half plus 1 by, so sorry, this will be cos, right? Integration of cos is, so it will be 1 by 4 pi sine 2 pi x from 0 to 1. And so this, because this is sine 2 pi is again 0 and sine 0 is 0, so this is basically half. So what we have got? So therefore, which implies the norm G is, so norm G will be square root of half, means 1 by root 2. And what we have to find? 2 norm G. So which implies 2 norm G, 2 norm G, 2 times 1 by root 2 is root 2. So what we have got? So this is 2 norm G is root 2. Okay, question number 8 is done. Let's move to the question number 9. What it is saying, let B be a finite dimensional linear product space over R and beta be a basis for B, then which of the following statements are true? If U inner product B is 0, then norm U square is less than norm of U plus AB for all A belongs to R. So let's check this. So what is U plus AB? U plus AB square, what is this? So this is, we know this is U plus AB, comma U plus AB, right? Then what it will be? Just expand the inner product. We'll get U inner product U plus A is a real number, so you will get UB plus A BU plus S square BB, right? This we will get. And these two are 0 because what it is given, UB are 0 and this is a real inner product space over R, right? So these two are 0. Note that these two are 0, right? So therefore what you will get? So you will get this is norm U square plus A square norm V square, right? So which is always greater than norm U square, right? So what we have got? So therefore what we have got? Norm of U plus taking the square root. This is greater than norm U square, norm U, right? So this we have to prove for all A in real number. So option number 1 is correct. Okay. Now what is option number 2? Let U be a belongs to B such that U inner product W equals to B inner product W for every W belongs to B. Then you have to show U equals to B. So this is true. So what is that? U inner product W equals to B inner product W for all W in B. Then U equals to B. So we'll prove this. So you have to prove this. So let's take this inner product. U minus B with W. What it will be? It will be U inner product with W minus B inner product with W. And these two are same, so this is 0, right? So this is true for all W in B. So in particular take, so let's me write this as the above expression is true for all W in B. So in particular, take W to be U minus B. Then what you will get? Then you will get U minus B, inner product U minus B is 0, which implies norm of U minus B. is 0 and norm 0 means the vector should be 0, right? U minus v should be 0, which implies u equals to v. So you prove that u equals to v. If union product w equals to v inner product w for all every w in v means u equals to v. What is question option number 3? For u v for u v u v in v, say that u not equals to w, you know u inner product w is not equals to v inner product w for some w belongs to v. Then u not equals to v, right? So let's check this option number 3. U inner product w is not equals to v inner product w for some w belongs to v. Then u not equals to v, right? So we will prove this. So let's assume that so now let's assume suppose we will prove this by contradiction. Assume u equals to v. Then what will happen? So if u equals to w, which implies u inner product w equals to v inner product w, right? For all w in v, right? Which is a contradiction, right? Because u not equals to, which is a contradiction to the hypothesis. Therefore, u not equals to v, right? So option number 3 is also correct. Now let's check the option number 4. Let v is in v, such that v inner product w is 0 for all w in v. Then you have to show v is 0, right? So option number 4. What it is saying? Given v inner product w is 0 for all w in v. You have to check v is 0 or not, right? So as early as this is true for all w in v, in particular take w to be v, right? Then what you will get? Then you will get v inner product v is 0, which implies norm v square is 0, which implies v is 0, right? So you get v is 0. So option number 4 is correct, right? This we have to prove. If v inner product w is 0 for all w is v, then v is 0. So this is also correct. Now let's check the option number 5. What did it say? Let x, y, z in v such that x inner product y equals to 0 and x inner product z equals to 0. Then is x inner product alpha y plus beta z is 0 for all alpha beta in R. So let's check this option number 5. So what it is given? Given for x, y, z in v such that x inner product y is 0 and X inner product Z is also 0. You have to check X inner product with alpha Y plus beta Z. Then what will happen to this? X inner product alpha Y plus beta Z, where alpha beta belongs to R. So what is so by the property of inner product, what will happen? X inner product alpha Y plus X inner product with beta Z. And this is a real inner product space, so alpha will come out X comma Y plus beta X comma Z, and these two are both are 0, so right, so we get this is also 0. So option number 5 is also correct. Now let's check this. Option number 6. Let U be in V such that U inner product W equals to V inner product W for some W is in the basis in beta, which is the basis. For some W is in, then U equals to V. So option number 6. What is saying? U inner product W equals to V inner product W for some W in the beta, where beta is a basis of B, right? Then U equals to V is true or not. So we will show that this is not true. So let's check this. So for example, let's do it on R2. On R2 we will do. So what we will take? On R2 1 comma 0 and 0 comma 1. These are the bases. So we take this to be beta is the basis of this. Take W to be suppose 1 comma 0. This is in the this is in the basis set. Now what will happen? Compute this 1 comma 0 with 0 comma 2 with usual inner product. Then what will happen? So this will be 0, right? 1 dot 0 plus 0 dot 2, it is 0. Similarly, what will be this? 1 comma 0 comma 0 comma 3. This is again 1 dot 0 plus 0 dot 3. This is again 0. Right? So if you call this to be U and this to be V. So let's do it another way. We have done it. We have taken. So for this is real inner product. This does not matter. But let's do as it is here. Take U to be 0 comma 2 and V to be 0 comma 3. Then U inner product W, what it will be? 0 comma 2, 1 comma 0. To do this inner product, what you will get 0 and V comma W, it is again 0 comma 3 comma 1 comma 0. It is again 0, right? But so this is true. This is 0 for W is in the basis, right? But U not equals to V, right? So therefore option number 6 is not correct. So you have shown UV is 0, U inner product W is V inner product W, but U not equals to V. So let me write it. Not here. These two are same, but U not equals to V, right? So option number 6 is false, right? Now what is option number 7? This let U be in V such that U inner product W is equal to V inner product W for all W in the basis. Then U equals to V. So we will show that this is true. So what is the difference with this 6 and 7? Here it is sum, here it is for all. So if this is for some vector in the basis, then it might not be true. But if this is for true for all vectors in the basis, then it is true, right? So we will show this. So option number 7. So U inner product V equals to, V inner product W for all W in V beta, right? Right. So we will show U equals to V. As beta is a basis of V, which implies span of beta is V, right? So if something is true for in the basis, then by the linearity it will true for, because this spans V, right? So therefore this will true for all vectors in V, right? Therefore U inner product W equals to V inner product W for all W in V, right? Because otherwise you will take any vector, and because this spans beta, so you can write it in the linear combination of the basis beta. Then by linearity you can show this. So this you can check, right? This is easy. And so we have shown in the option number. So then by the option 2 we are done, right? Then by the option 2 we get E equals to V, right? So option number 7 is done. So therefore we will get, if this is true for all W in the basis, then U equals to V. So option number 7 is also correct. Okay. So I think this is the last question of this assignment. So you have finished the assignment 9. Okay. Okay, so let's stop for today. We'll meet in the next week. Okay, thank you. Bye.